May 27, 1940, a telegraph landed on the desk of William Knudsen, the president of General Motors, summoning him to Washington with a message so urgent it carried no pleasantries, no preamble, and no room for negotiation. The message had come directly from the White House. Franklin Delano Roosevelt needed to see him immediately. The country, though not yet formally at war, was watching Europe burn from across the Atlantic, and the men in Washington had done the arithmetic. They knew what was coming, and they knew that when it arrived, America would not be ready. Knudsen arrived at the White House to find a president who was not interested in small talk. Roosevelt sat behind his desk, already deep in conversation with military advisors and industrial consultants. Charts and production figures spread before him like a general's battle maps. He looked up at Knudsen, this broad-shouldered Danish immigrant who had risen from the factory floor to the executive suite, and told him plainly that the United States needed airplanes. Not dozens, not hundreds, thousands, tens of thousands, perhaps more than the world had ever seen produced in such a concentrated span of time. Roosevelt wanted 50,000 aircraft per year. The room went quiet. Some of the men present later admitted they thought the president had misspoken. He had not. What followed over the next 4 years was one of the most extraordinary industrial transformations in the history of human civilization. It was not clean. It was not always efficient. It was built on the backs of workers who had never touched a rivet gun, engineers who had to invent solutions before they could even fully articulate the problems, and executives who had to abandon everything they knew about manufacturing and rebuild their understanding from the ground up. But when the final accounting was done, when the last propeller was bolted and the last fuselage was painted, the United States had produced more than 300,000 military aircraft. The number is almost too large to hold in the mind, and yet it happened. This is the story of how. To understand what America was being asked to do, it is necessary to first understand how small the American aviation industry was in 1939. At the dawn of the war in Europe, the United States Army Air Corps possessed fewer than 2,000 aircraft considered combat-ready, and many of those were already outdated by the standards of modern aerial warfare. The entire American aircraft manufacturing workforce numbered somewhere around 60,000 people, a figure that would have been dwarfed by the labor force of a single large automobile plant. The factories themselves were modest operations, often tucked into modest hangars in California and the Pacific Northwest, producing aircraft in numbers that would have seemed almost quaint against the backdrop of what the Luftwaffe was assembling across the ocean. The aviation industry at that time was fundamentally a craftsman's industry. Aircraft were complex, hand-assembled machines. Skilled workers bent aluminum, shaped ribs and spars, and fitted components with the kind of patient precision more associated with watchmakers than with assembly line workers. A completed fighter might require hundreds of hours of skilled labor, a bomber thousands. Each aircraft was almost an individual object, built in relatively small numbers, with engineers and workers intimately familiar with every system. It was not an industry designed for mass production. It was not even an industry that had seriously considered the possibility. The war changed everything. When Germany invaded Poland in September of 1939, and when France fell with stunning speed in the summer of 1940, the men in Washington, who had been watching the conflict with careful eyes, finally found their fears confirmed. The Luftwaffe was not a rumor. The Messerschmitt Bf 109 was not propaganda. German air power had proven itself a genuine and devastating force, and America, sitting behind its ocean walls and its doctrine of neutrality, possessed nothing close to an equivalent force. Even the British, battered but unbowed in the skies over their own island, were already begging Roosevelt for materials and aircraft. The need was not theoretical. It was immediate. Roosevelt's 50,000 aircraft demand struck most experts as impossible. The United States had produced fewer than 6,000 aircraft of all types in 1939. To leap from 6,000 to 50,000 in a single year would have required multiplying the entire industry nearly 9 times over. Not just the factories, but the workers, the materials, the machine tools, the supply chains, and the engineering capacity to design aircraft fast enough to stay relevant in a war that was evolving by the month. In April of 1940, even before Knudsen's meeting with Roosevelt, The Army and Navy had jointly concluded that the maximum realistic production capacity of American industry was around 12,000 aircraft per year. Roosevelt had asked for more than 4 times that, and yet the men who were tasked with achieving the impossible did not despair for long. They rolled up their sleeves. The first and most critical decision made by American planners was one that seems obvious in retrospect, but was deeply controversial at the time. Rather than allowing the aviation industry to expand organically, building new aircraft factories from scratch, hiring more specialized workers, training more aeronautical engineers, the government made a decision of breathtaking audacity. They would bring in the automobile industry. This was not a universally popular idea. The aviation manufacturers, companies like Boeing, Douglas, Lockheed, Grumman, and Consolidated, were deeply protective of their expertise. They had spent decades developing the knowledge and skills that went into building aircraft, and they were skeptical that men who spent their days building Fords and Chevrolets could simply be handed blueprints and told to manufacture something as complex and unforgiving as a fighting aircraft. The two industries were fundamentally different, or so the argument went. An automobile could be imperfect in ways a military aircraft could not. A car with a slightly misaligned door was an inconvenience. A bomber with a structural flaw was a coffin. But the automobile manufacturers looked at the problem differently. They looked at aircraft as a manufacturing challenge, not a mystical craft. And they had something the aviation industry desperately lacked: experience in organizing enormous industrial systems to produce complex products at extraordinary speed and volume. Henry Ford had not invented the assembly line, but he had perfected it into a philosophy of production. And that philosophy, his former colleagues and competitors believed, could be adapted. The critical insight was this: if an aircraft could be broken down into components, and if those components could be standardized to the point where they could be manufactured identically and at scale, then the final assembly of an aircraft was not fundamentally different from the final assembly of an automobile. The challenge was immense, but it was a manufacturing challenge. And manufacturing was something Detroit knew. William Knudsen became one of the central architects of the industrial partnership between Detroit and the aviation world. He understood both industries, having risen through the automotive world while maintaining a deep respect for precision engineering. He worked to establish what became known as licensed production agreements, in which major automotive companies would be given the rights to manufacture aircraft designed by aviation companies. Ford would not design its own bomber. Ford would manufacture the B-24 Liberator, a design that had come from Consolidated Aircraft in San Diego. Using Ford's manufacturing genius to produce it in numbers Consolidated could never have managed alone. This arrangement required an almost philosophical renegotiation of what manufacturing meant. Aviation blueprints, which had previously been treated as living documents that engineers adjusted constantly as they built each aircraft, had to be frozen and formalized with a precision that the industry had never before demanded. Every component had to be documented to tolerances that could be replicated in a factory in Ypsilanti, Michigan, by workers who had never been near an aircraft. This was harder than it sounds. Aviation engineers, accustomed to making intuitive adjustments as they worked, sometimes struggled to articulate in writing the knowledge that lived in their hands. But the work was done. The most famous symbol of what American industry was capable of when fully committed to aviation production was a building. Not an aircraft, a building. The Willow Run Bomber Plant, constructed by Ford Motor Company on farmland west of Ypsilanti, Michigan, was, at the time of its completion, one of the largest manufacturing buildings in the world. It stretched for nearly a mile. Its floor space covered more than 3 million square feet. Standing inside it for the first time, workers described a sensation of disorientation, as if they had walked into an enclosed landscape rather than a factory. The building's enormous L shape had been designed in part to avoid crossing county lines, a quirk of local tax law that forced the engineers to bend the assembly line rather than let it run straight, a compromise that itself became a minor engineering challenge to manage. Within those walls, Ford planned to build B-24 Liberator heavy bombers at a rate that its critics called impossible and its advocates called inevitable. In the beginning, Willow Run struggled badly. The transition from automobile production to aircraft manufacture was harder than even the skeptics had anticipated. The tolerances required for aircraft components were far tighter than anything the automotive workers had experienced. Tools had to be specially made. Processes had to be invented. Workers who could operate a stamping press with their eyes closed had to be retrained almost from scratch, learning to work with new materials, new instruments, and new standards of precision. In 1942, Willow Run produced a deeply disappointing number of aircraft, far below what had been promised. Critics and the press took to calling it Will It Run, a nickname that stung because it captured a genuine anxiety that the whole enterprise might be a costly mistake. But the plant did not give up. Ford threw engineering talent and management expertise at the problem with the kind of organizational ferocity that the company had developed over decades of competitive production. Workers became more proficient. Processes were refined. The assembly line, once chaotic and unpredictable, began to find its rhythm. And then, in the latter half of the war, Willow Run began to deliver on its promise in a way that stunned even those who had believed in it. At its peak, the plant was producing a completed B-24 Liberator every 63 minutes. Let that settle for a moment. Every hour, a 4-engine heavy bomber, a machine of almost incomprehensible complexity, carrying thousands of individual components, wired for electrical systems, armed with turrets, fitted with oxygen systems for high-altitude flight, rolled out of the Willow Run plant and prepared to join the war. By the end of the conflict, Willow Run had produced more than 8,000 B-24 Liberators, more than any other single facility in the world. The building that had once been called a failure had become the most productive bomber factory in history. But Willow Run was only the most famous example of a transformation that was happening across the entire country simultaneously. From the West Coast to the Gulf of Mexico, from the Great Lakes to the plains of Kansas, American industry was being reshaped around the single overriding purpose of aerial supremacy. In Seattle, Boeing was expanding its workforce at a rate that strained the capacity of the surrounding region to house and feed its new employees. The B-17 Flying Fortress, already one of the most capable bombers in the world when the war began, was being produced in numbers that its original designers would have found extraordinary. Boeing's engineers worked in a state of controlled urgency, simultaneously manufacturing the aircraft in its current form while designing improvements that could be incorporated into future production runs without stopping the line. This was an almost impossible balancing act, modifying a design while manufacturing it at scale, but the engineers found ways to manage it, using block production systems that allowed changes to be introduced at set intervals rather than continuously, giving the factory floor time to adjust before the next modification arrived. In Burbank, California, Lockheed was producing the P-38 Lightning, one of the most distinctive and capable fighter aircraft of the war. The twin-boom, twin-engine P-38 was an unconventional design that offered remarkable range and performance, and it became one of the most important American aircraft in the Pacific Theater, where its long legs made it invaluable for escort missions across vast stretches of open ocean. Lockheed's workforce, like those at plants across the country, grew with extraordinary speed. Workers were recruited from agricultural communities in California and from cities across the Midwest, drawn by the promise of steady wages and the sense, genuine, not manufactured, that they were building something that mattered. In Bethpage, New York, Grumman Aircraft Engineering Corporation was producing the F-6F Hellcat, the Navy's answer to the Japanese Zero. The Hellcat's design story is a testament to the speed at which American aviation was moving. The aircraft went from its first design conference to its first flight in less than 18 months, a pace of development that would have seemed reckless before the war, but was now simply the normal tempo of an industry operating at emergency speed. The Hellcat would go on to destroy more Japanese aircraft than any other Allied fighter in the Pacific, and it was produced in numbers that the Japanese aviation industry, for all its brilliance, could not match. The question of who was doing this work deserves its own careful attention, because the answer upended social structures that Americans had assumed were permanent. Before the war, American manufacturing, and aviation manufacturing in particular, was an overwhelmingly male domain. Women worked in offices, in service industries, and in certain light manufacturing sectors, but the factory floor of a major industrial plant was understood to be a man's world. The tools were designed for men's hands. The culture was shaped by men's expectations. And when the war began pulling millions of men out of the workforce and into uniform, the question of who would fill those factory positions became suddenly, urgently pressing. The answer came in the form of one of the most dramatic workforce transformations in American history. Women entered the aviation industry in enormous numbers, learning to rivet, to weld, to operate drill presses and hydraulic presses, to wire electrical systems and install hydraulic lines. The iconic image of Rosie the Riveter, that determined, capable figure with her sleeves rolled up and her jaw set, was born directly from the aviation industry, where women were doing exactly that work, in enormous numbers, with remarkable proficiency. The women who entered aviation manufacturing were not treated as temporary novelties or as a last resort. They were trained, organized, and integrated into the production system because the system could not function without them. Many of them discovered, with what must have been a complicated mixture of pride and frustration, that they were excellent at the work, often better than the men who had preceded them. Their hands were sometimes better suited to the tight spaces inside aircraft fuselages, and their attention to detail and tolerance for repetitive precision tasks made them exceptionally effective in quality-critical manufacturing environments. By 1943, women made up close to 40% of the workforce at many major aircraft plants. African American workers also entered aviation manufacturing during the war years, though their experience was shaped by the racial segregation that remained brutally present even in wartime. Many aviation plants, particularly in the South, maintained segregated facilities and restricted black workers to the lowest skilled and lowest paid positions. In other regions, particularly on the West Coast and in the North, black workers were able to access a wider range of positions, and some aviation facilities, pushed by both economic necessity and, increasingly, by government pressure, began to integrate their workforces in ways that represented genuine, if incomplete, progress. The wartime aviation industry was not a story of racial equality, but it was a moment in which the contradictions of American racial hierarchy were placed under unusual pressure, with long-term consequences that would not fully unfold until after the war was over. Children and elderly workers, retired craftsmen who had spent decades away from factory floors, immigrants who spoke little English but understood machines with an intuitive fluency that needed no translation. All of them became part of the enormous human engine that was building American air power. The workforce of American aviation expanded from approximately 60,000 workers in 1939 to more than 2 million at the peak of production in 1943 and 1944. 2 million people, the vast majority of whom had never built an aircraft before. The materials that went into those aircraft had to come from somewhere, and the logistics of supplying an industry of that scale required a mobilization effort nearly as impressive as the manufacturing itself. Aluminum was the central material challenge. Aircraft are made primarily of aluminum, strong, light, and workable in ways that made it the essential metal of the aviation age. But aluminum production in the United States in 1940 was nowhere near adequate for the demands that were about to be placed on it. Expanding aluminum production required enormous quantities of electrical power, since the smelting process is extraordinarily energy-intensive, and it required the construction of new smelting facilities at a speed that would have seemed impossible under normal economic conditions. The government addressed this through a combination of public investment and aggressive coordination with private industry. New aluminum smelting facilities were constructed in the Pacific Northwest, where the Columbia River and its network of dams could provide the hydroelectric power the process demanded. Existing facilities were expanded, and across the country, scrap metal drives, those familiar wartime rituals of patriotism, collected aluminum in quantities that, while symbolically important, were ultimately less significant than the massive new industrial infrastructure being built to supply the factories. The aluminum supply chain, stretched nearly to its limits for much of the war, somehow kept pace with production demands, though it never offered the comfortable margins that planners would have preferred. The engines that powered those aircraft presented their own immense manufacturing challenge. A single radial aircraft engine, the powerful air-cooled engines that drove most American propeller aircraft, contained thousands of precisely machined components, many of them operating under conditions of extreme heat and mechanical stress. Manufacturing these engines required machine tools of extraordinary precision, operated by workers with specialized skills that took months to develop. The Pratt & Whitney R-2800 Double Wasp, one of the most important aircraft engines of the war, powered aircraft as different as the F-6F Hellcat, the F-4U Corsair, the B-26 Marauder, and the P-47 Thunderbolt. Producing it in the numbers the war required demanded a manufacturing network that extended across multiple states and dozens of supplier companies, each responsible for particular components that had to be made to tolerances measured in thousandths of an inch. The propellers that converted all that engine power into thrust were themselves complex manufactured objects, and their production was another bottleneck that required careful management. Hamilton Standard, the dominant propeller manufacturer, developed the constant speed propeller, a device that automatically adjusted its blade pitch to maintain optimal efficiency across a range of flight conditions, and manufacturing this device at scale was a significant industrial achievement in its own right. Problems in propeller production could cascade through the entire aircraft program, creating delays and inventory imbalances that planners spent enormous energy trying to anticipate and prevent. The design offices that were creating the aircraft these factories were building were operating under a pressure that is almost impossible to fully appreciate from the comfortable distance of the present. Aircraft design in peacetime is a process measured in years. A design concept is evaluated, refined, and tested through an extended cycle of engineering analysis, wind tunnel testing, prototype construction, flight testing, and iterative improvement before an aircraft enters production. The process is slow because the stakes are high. An aircraft with a significant design flaw will kill people, and the methodical pace of peacetime development is the mechanism by which those flaws are found and corrected before pilots put their lives in the machine's hands. The war compressed this process to a degree that terrified many experienced engineers. Aircraft were going from initial design to production in months. Changes were being incorporated into production aircraft in flight, literally. In some cases, with modification kits being fitted to aircraft that were already in service. The B-29 Superfortress, the enormous strategic bomber that would ultimately deliver the atomic bombs that ended the war in the Pacific, was so complex and so rushed in its development that it arrived in combat with serious engine cooling problems that caused fires and crashes before the issues were identified and addressed. The men who flew the early B-29s knew they were testing the aircraft as much as operating it, and they flew with a courage compounded by that knowledge. Yet the design offices also produced, in this compressed and desperate period, some of the most capable aircraft in history. The North American P-51 Mustang stands as perhaps the most celebrated example. Originally designed in response to a British requirement, the early versions of the Mustang were powered by an Allison engine that gave it reasonable low-altitude performance, but left it gasping at the altitudes where bomber escort missions took place. The transformation came when someone, the British deserve credit for the initial insight, suggested fitting the airframe with the Rolls-Royce Merlin engine, which Packard was already manufacturing in the United States under license. The result was one of those rare moments in engineering when two good things combined to make something transcendent. The Mustang with the Merlin engine was not just better than the Allison-powered version. It was, by the judgment of many who flew against it, the finest piston-engine fighter aircraft of the Second World War. It had the range to escort bombers all the way to Berlin and the performance to defeat whatever the Luftwaffe sent up to challenge it. The P-51 was designed in about 117 days. The engineering history of the war is full of achievements like this. Aircraft conceived, built, tested, and sent into combat in time frames that would be considered recklessly compressed even today, and that would have been considered utterly impossible before the emergency of the war redefined what was possible. The men who tested those aircraft occupied perhaps the most extraordinary professional position of the war, tasked with taking new machines into the air before anyone had fully established whether those machines would bring them back down safely. Test pilots at facilities like Wright Field in Ohio and at the manufacturer's own airfields were the first human beings to discover what a new design would do at extreme altitudes, or in a high-speed dive, or when one engine failed. They were not reckless men. They were, by and large, meticulous and analytical, approaching their work with the same careful engineering mindset that the designers in the offices below them brought to their calculations. But they were also men who accepted, with a clarity that most people prefer not to achieve, that any flight might be their last. The testing process was not safe. Aircraft were lost, and pilots with them, in numbers that the war's vast carnage makes easy to overlook, but that represent individual tragedies of the sharpest kind. What the test pilots found in these aircraft sometimes required immediate and fundamental redesign. The phenomenon of compressibility, in which an aircraft approaching the speed of sound would encounter aerodynamic forces that the pilot's controls were powerless against, was discovered and relearned in terrifying ways during high-speed dive tests in the early 1940s. Pilots who survived these encounters described their aircraft as entirely unresponsive, plunging toward the ground with the controls frozen or reversed, the speed building with a kind of cold inevitability. Understanding this phenomenon and engineering solutions that gave pilots a fighting chance to recover from it required not just courage from the test pilots, but a genuine scientific advance in the understanding of high-speed aerodynamics, an advance achieved under fire by engineers working at the frontier of a science that was itself barely 30 years old. The National Advisory Committee for Aeronautics, the NACA, the predecessor to NASA, played a crucial and often underappreciated role in this process, operating research facilities at Langley in Virginia, at Ames in California, and at Lewis in Ohio. The NACA's engineers and scientists worked throughout the war to advance the fundamental understanding of aerodynamics and aircraft performance, translating their findings into practical guidance for the industry in a way that significantly improved the aircraft coming off American production lines. The low-drag laminar flow wing, developed in part through NACA research, gave the P-51 Mustang a significant portion of its exceptional range by reducing aerodynamic drag far below what earlier wing designs could achieve. The aircraft that emerged from all of this, the factories, the workers, the designers, the test pilots, and the researchers, arrived at the front in numbers that changed the character of the war. The shift in the air war over Europe in early 1944 is one of the most consequential turning points of the entire conflict. German bomber production had been substantial. German fighter production was formidable. The Focke-Wulf 190, the Messerschmitt 109, the Junkers 88. These were serious aircraft, flown by pilots whose training and experience, particularly in the early years of the war, were formidable advantages. The bombing campaign against Germany in 1943 had inflicted terrible losses on American bomber crews, losses so severe that some doubted whether the campaign could continue at all. The Schweinfurt raids of October 1943, in which unescorted B-17 formations suffered losses that would have been unsustainable had they continued at that rate, represented a genuine crisis of strategic air power. What changed it was the P-51 Mustang, arriving in sufficient numbers and with sufficient range to escort the bombers all the way to their targets and back. But the Mustang could not have changed the air war alone. It was the sheer volume of aircraft arriving from American factories, replacing losses faster than the Luftwaffe could inflict them, flooding the theater with machines and pilots in a tide that German industry, for all its impressive wartime production, could not match. That ultimately decided the contest. By the spring of 1944, the Luftwaffe was being ground down not because its pilots were less skilled or its aircraft less capable, but because American production had created an arithmetic of attrition that Germany could not survive. Every German pilot who was shot down and killed represented an irreplaceable loss of training and experience. Every American pilot who was shot down was replaced by one from a training system that was producing aviators in thousands, trained on aircraft produced in the same factories that were simultaneously supplying the front. In the Pacific, the story was similar in its broad outline, though different in its specific texture. The Imperial Japanese Navy's aviation arm, which had entered the war with some of the most skilled and experienced carrier pilots in the world, was bled white at the Coral Sea, at Midway, and at the long attrition of the Solomons campaign. Japan's aviation training system could not replace those losses fast enough, and American production was simultaneously delivering aircraft of increasing capability: the Hellcat, the Corsair, the Avenger, and eventually the B-29, in numbers that overwhelmed the Japanese ability to contest them. By 1944, American fighters and bombers ruled the Pacific skies in a way that would have seemed like fantasy to the men who had watched the smoke rise from Pearl Harbor 3 years before. Behind the numbers, behind the 300,000 aircraft and the 2 million workers and the billions of dollars of production, there are individual stories that give the statistics their human weight. There was the woman on an assembly line at Lockheed in Burbank who was told by her supervisor on her first day that she would be fitting rudder cables in the tail section of P-38s, a job that required working in an almost impossibly confined space, lying on her back and reaching above her head for hours at a stretch. She was small enough that the work suited her. She became one of the most productive cable fitters in the plant. Her name was not recorded in the factory's official histories, and there were thousands like her. There was the Boeing engineer in Seattle who, in the winter of 1942, identified a potential fatigue cracking problem in the wing structure of the B-17 at a point where two components were joined. The discovery threatened to force a production halt that the Army desperately needed to avoid. The engineer worked through 3 consecutive nights with a small team, developing a redesigned junction that eliminated the problem and could be incorporated into the production line without stopping it. The fix worked. The aircraft continued to roll out. The engineer received a letter of commendation and went back to the next problem. There was the 19-year-old from rural Alabama who had never been more than 20 miles from the farm where he grew up, who found himself working a lathe in a defense plant in Birmingham, making landing gear components for fighters. He sent money home to his family each week, more money than his father had seen in a year of farming, and he worked 12-hour shifts with a focus and a pride that his foreman described, in a letter to the plant manager, as exceptional. He was not exceptional in any statistical sense. He was entirely typical of the workforce that built American air power. Young, adaptable, deeply motivated, and completely without previous experience of what they were now doing with a competence that astonished everyone, including themselves. There was the Japanese-American man who had been released from the internment camp where his family had been imprisoned, who went to work for an aircraft manufacturer on the West Coast because the alternative was to remain behind the wire. The contradiction was not lost on him, nor on the plant workers around him, who responded to his presence with reactions ranging from suspicion to solidarity. He worked. He produced. He built aircraft that were fighting a war against the country of his ancestry, in defense of a country that had locked away his family, because the complexity of loyalty and identity and belonging does not resolve itself into clean formulas even in moments of national emergency. These stories, and there were 2 million variations of them, each with its own texture of sacrifice and adaptation and discovery, are the human reality that the production statistics represent. There were also failures, miscalculations, and moments of genuine institutional dysfunction that complicate the narrative of seamless industrial triumph. The Douglas XB-19, one of the largest aircraft of its era, had been under development for years and was ultimately irrelevant to the war. The resources poured into it might have been better used elsewhere. The early production problems at Willow Run were genuinely serious and reflected real organizational failures, not merely growing pains. There were contract disputes between manufacturers and the government that created delays. There were instances of labor unrest at production facilities that temporarily slowed output. There were quality control failures, aircraft leaving factories with defects that should have been caught, some of which proved dangerous when encountered in combat. The system that managed all of this was itself an improvised creation, assembled at speed from the materials that American government and industry had available. The War Production Board, established in January of 1942, attempted to coordinate the entire American industrial mobilization, making decisions about which industries would receive materials and which would be required to defer to more urgent priorities. Its authority was frequently contested, its jurisdiction overlapped with that of other agencies, and its leadership changed often enough that institutional continuity was a constant challenge. The men who ran it were capable, but they were navigating territory that had no map. What ultimately made the system work, despite its inefficiencies and contradictions, was something that is difficult to quantify but impossible to ignore in the historical record. The workers, the engineers, the executives, and the government officials who were building American air power believed with a conviction that went beyond ordinary professional motivation that what they were doing mattered absolutely. They understood, even those far from the front who had only an abstract understanding of combat, that the aircraft leaving their factories would determine whether free people or tyrannical states shaped the world their children would inherit. This was not always articulated. It was often simply felt, as a weight behind the workday, as a reason to take the extra minute to get a component right, as a source of endurance in the face of exhaustion and frustration and the grinding repetition of factory labor performed for months and years on end. The moral stakes were, to the people living them, entirely real. And that reality powered the machines as surely as the aluminum and the engines and the engineering. By the summer of 1945, the numbers had accumulated to their final form. 300,000 aircraft, bombers and fighters and transports and trainers and reconnaissance aircraft, of dozens of types, produced at facilities spread across a country that had turned its peacetime economy inside out and rebuilt it around this single colossal purpose. The men and women who had built them were beginning to hear talk of reconversion, of the factories returning to civilian production, of the wartime contracts winding down, of the jobs that would eventually disappear as the emergency passed. For many of them, the feeling this produced was complicated. The work had been hard, often physically punishing, monotonous in its daily texture, even as it was epic in its larger meaning. They were tired. They missed the people they had left behind or who had been taken from them. They wanted to sleep late on a Sunday morning and not think about production quotas or shift schedules or whether the component in their hands met tolerance. And yet there was something else, a pride so deep and so justified that it required no performance, no rhetoric, no ceremony. They had done something that most of them would never have believed possible before the emergency of the war stripped away the assumption of impossibility and replaced it with the simple question of how. The aircraft they built flew in every theater of the war. They flew over the desert expanses of North Africa and the frozen fjords of Norway. They flew from the deck of carriers in the middle of the Pacific, disappearing into the horizon on missions from which not all of them returned. They flew through flak over Germany, through monsoon clouds over Burma, through the crystalline high-altitude air above the Japanese home islands. They were flown by men from Texas and Ohio and New York and California, by men from Britain and Canada and Australia and France, by men who had grown up with flight and men who had encountered it for the first time when the war placed them in a cockpit and told them to learn. They were maintained by mechanics who worked in the mud and the heat and the cold with a devotion to their machines that bordered on the personal, because they understood that their mechanical skill was the only protection available to the pilots who trusted those machines with their lives. 300,000 aircraft. It is a number that invites reduction, a statistic, a data point in the industrial history of a war. But each one of those aircraft was a physical object, assembled by human hands, out of materials dug from the earth and refined and shaped and fitted together with precision and care. Each one was a decision made, a problem solved, a challenge met by people who had no previous experience of what they were being asked to do and who did it anyway, because the world had presented them with a requirement that admitted no alternative. The factories have long since been converted or demolished. The aircraft themselves, of the 300,000, only a relative handful survive, preserved in museums where visitors walk past them and try, usually unsuccessfully, to fully grasp what they represent. The workers who built them have nearly all passed from the scene. The generation that accomplished this thing is almost entirely gone now, taking with them the memory of what it felt like to stand on a factory floor in 1943 and know that the object taking shape before them was a weapon in a struggle for the future of civilization. What they left behind were the aircraft and the knowledge, available to those who look for it, that when a free people face an existential challenge and commit themselves to meeting it with everything they have, what they can accomplish exceeds what any of them, beforehand, would have dared to predict.